All right. The size p of a certain insect population at time t in days obeys the function. There it is. So we're talking about exponential growth in decay. So we're going to put this in real life. I like this. I like when it's real. The more real it is, the more interesting it is to me. So this is real. This is biology, you know, and how they figure the growth of populations, whether it be an E. coli in a petri dish or insects or rabbits in the field. You know, it's the growth of populations grow exponentially unless, well, they grow exponentially if there's no predators and no environmental restrictions as far as space and food supply and water. Then they will grow exponentially. But in reality, there's predators and there's other things. You've heard those stories, right? About interesting stories from history where they take a certain kind of rabbit or something and they transplant it to a new island it's never been on before.
Transplant.
Yeah, and they bring it in where it's got no predator and it takes over the island. That's happened historically. You heard about that? Yeah. Back when, you know, like back when they were first doing ship travel between islands, right? Sometimes they would grab some animals from one island and they would bring them back with them to their home island. It happened in Ireland or one of those places. And there was some kind of rabbit or something. The most famous was some kind of rabbit or something that they brought 10 of them or whatever back to this island from some new island. They brought it back. This kind of rabbit had never been on this island before that they brought back home with them. And there was no predator there. I don't know what the foxes or hawks or whatever weren't there. Their natural predator wasn't on that island. So the rabbits took over. They started breeding and eating and growing, and there was no predator. There was plenty of food. It was an agricultural island. And they started mowing the place down. You can type into Google or something, you know, rabbit population takes over or whatever, and you'd find the story. It was like the 1800s or something, I can't remember when. And it was they just started mowing it down. I mean, they became like millions of rabbits. And they would just come onto farmers' fields like locusts, you know, and they would just take it out because, you know, there was no predator. And so the farmers had to go out with their guns and just in thousands just kill the rabbits because they were taking over. Yeah, I don't know. Probably interesting stuff. But anyway, so that's what this formula is. Yeah, if there's no predator, remember, because when you look at this, you should think exponential. That's wow, right? Remember, exponential rockets up. Do populations really go like that? Yes, if there's no predator and no space restrictions and no food or water restrictions, yes, they will, but not with predators and stuff. All right, so with that said, let's crank it out. Determine the number of insects at 0 days. So that's just plugging a 0, right? Just take it, yeah, right, exactly. So P of t is 100 e to the point 06t. You don't need that other 0 in the front. Plug in the 0 for time, and you get 100 e to the 0.06 times 0. Anything to the 0 power, e to the 0 power is 1. That's 100 times 1. That's just 100. Exactly. That number in the front is the initial amount. It's like the principal. It's like the PERT formula. This is basically the PERT formula. I'm going to use PERT. Just think about it as money. What is that? That's the principal investment. That's the money you put in first. That's the number of insects at first. Same thing. The insects are growing in the bank. Same thing. Same idea. Same math behind the insects and the money. Same thing. All right. Part B. That's part A, part B. So you didn't even need to do all that work. You can just do what Raul did and just say it's 100. Yeah. Right. Part B. What is the growth rate? The growth rate is the rate. What's the interest rate? 6%. Exactly. 0.06, but they want a percentage, so make it 6%. Totally. It's just like the PERT. Just pretend that's the PERT formula. This is the P. This is the R. It's exactly the same. Money, animals, insects, whatever, same thing. What is the population after 10 days? Plug in a 10. Time is 10. Right? T is in days. See up here? T is in days. Plug in 10. So the population will be 100 e to the 0.06 times 10. Put in a 10 there. Just use your calculator. 100 times e to the, what is that going to be? I'm going to get 182. 182 point, how many? They probably just want me to round to the nearest whole number. We don't want part of an insect. 182. 182 little critters after 10 days. Little insects after 10 days. Good so far? So just plug in 10, move on to part C. Part C, or that was D, part C, now let's go to D. When will the insect population reach 150? So let's write P. We just keep using this formula again and again and again. 0.06T. Now they're saying when, so they want T, don't they? When will it reach 150? So what do we do with that 150?
Plug in 150 for T.
Yeah, that's like the amount. Right? You can just say it's the amount for you. You want your bank account to become 150. You want your number of insects to be 150 later. So solve for T. So what am I going to need to do to solve for T there?
The ln thing.
ln thing, because T's in power, right? Divide by the 100, then ln both sides. You've done a lot of these now, and you're comfortable with them, right? That's 1.5 e to the 0.06t. ln. Bring this down. So this is ln 1.5. 0.06t ln e. ln e is 1. So that's gone. Just divide by the 0.06. Boom, boom. So I'm getting ln 1.5 divided by 0.06. I'm getting 6.75.
Yep.
75, 77, whatever. And that's that's time in days. So I don't know how far they want you to round it, but that's how many days until the insect population hits 150. And then E, when will the insect population double? So we good to there so far? When will it double? Let me just write up here for double.
So 200.
So part E, so this down here was part D. So when will it double? So again, using the same formula, population is 100 e to the 0.06t. So for doubling, what do you do?
Just multiplying the 100 by 2. Okay.
Yeah, you just say you want the population to be 200. Because remember, it started at 100, right? So you want the amount to be 200. You want the number, and you just solve for t again. Just go on and solve for t. Is that okay? There we go. It's going to be close to 12 years, isn't it? 12 days, I mean. Because remember the rule we use, the doubling rule for money? Set rule 72, I told you. The growth rate is 6%, times 12 would be 72. 11.5 is close to 12 days. You can expect the answer for the insect population to double. So every 12 days, that insect population will double if you don't bring it under control. Pesticides are good. What do they say in India? The rats and the cows are worshipped. Thus, the effect, they don't use pesticides. They're changing their ways, for which I'm thankful. But they let the rats run a little. They did for many years in India, let the rats do whatever the rats wanted to do. They ate 30% of the food supply every year because they were not controlled, and people are starving in India. They're letting the rats eat 30%.
They eat like
So they grow, I think, maybe. So we'll do the hard ones tomorrow. Strontium 90 is radioactive material that decays. Okay, so we got that formula. What is the decay rate? So now we're talking, instead of growth, we're talking about decay. So we're talking about you take a chunk of this strontium stuff and you just leave it out, it starts going away, goes into the atmosphere, right? It starts slowly going away. How fast does it decay? How fast? So it's the opposite of exponential growth. It's exponential decay. Here's the formula. They're giving me the formula. So it's A0 e to the negative, what is that? 0.0244 t. You see that negative? Or let me put it up here. That's what tells you it's decaying. Negative power on the E means decay, not growth. So that's the difference between exponential growth and exponential decay. Growth has a positive power. Decay has a negative power. It makes it go down. Remember, negative exponential functions come down for a landing at their horizontal. Remember the graphs at their horizontal. So this one's going to flatten out. Okay. The A0, remember, just if this confused you at all, just remember the PERT formula. It's really still the PERT formula. So what's the A0? It's like the P. It's like the principal investment in a bank account. It's just the money you put in it first. So just always remember the PERT. That's all these are. These are all just fancy versions of the PERT. They're going to call them by different letters and stuff, and I know that can be confusing. So that's why I'm reminding you of the PERT, so that you won't be as confused. So this A0, it's just P. It's just the principal. It's the amount of the strontium at first. That's what it is. It's the amount, the chunk that was originally there, and then over time, that'll get less and less as it decays and heads off into the atmosphere. Does that make sense? They always call it in science formulas, biology, chemistry, all those, they'll put a sub-zero there. That means at time zero. So you want to get used to that. Biology, chemistry, you always see they'll put such and such with a sub-zero, a low-down zero like that. That zero means time zero, initially, in other words. In other words, it's like the principal. It's the money you put in the bank at first. It's the amount of strontium you had at first. Initial amount. That's all that is. You don't have to plug in that zero or anything. Just know they're saying that's the initial amount at time zero. Okay. So what is the decay rate? Well, the rate's right here, isn't it? That's the rate. Remember the PERT thing? That's the rate, and so that's 0.0244. Change it into a percentage. Move it 2 places. 2.44%. So that means 2.44% of it is going away every, whatever, I don't know what the time is. Oh, year. Time is in years. Every year, 2.44% of this strontium stuff goes away. How much strontium 90 is left after 20 years? Well, A0 e to the minus 0.0244. Plug in 20 years, right? For time. Plug in 20. Now, what am I going to put in for the A0?
500 grams.
Yeah, that's the initial amount. Good job. That's the 500 grams, right? Assume that a scientist has 500 grams at the start. So that's the A0. It's 500 e to the minus 0.0244 times 20. And then you can hit the buttons. We are running out of time rapidly, aren't we? What is the life? Oh. All right. We will stop